Welcome back, everyone. Hopefully you enjoyed the lunch. And now we are going to start the sessions of the afternoon. So we have 3 talks. The first one is Dino, who is a postdoc at UCL, and he's going to be talking about hypothesis testing and feature selection with kernels.
Thank you very much, Fernando. It's a pleasure to be here. Very exciting workshop. Thanks very much to the organizers for all the hard work that you put in. Looks like a very, very good place to be, and I'm looking forward to all the discussions that we'll be having over the day. So, should I just switch this better? Oh, okay. Cool. So, I'm a postdoc at the Gatsby unit at the UCL. So, I do research at the interface between statistics and machine learning. I think of myself more as a statistician than a machine learner. But I've recently been dragged to the Shogun community by Heiko, who's also working at the same institute as I, where I was mentoring a project for the Google Summer of Code, and I will be basically discussing the topic of this project in this talk. So I'm interested in general in kernel methods. We've seen tutorial on kernel methods, very nice tutorial by Marius. But I'm also interested in statistical machine learning, in basically using the ideas that arise in sort of classical kernel methods in machine learning to solve fundamental statistical inference tasks, to pose non-parametric hypothesis tests for the two-sample problem for independence, and also to see how these embeddings of probability distributions into these Hilbert spaces can basically aid in inference. For example, they can aid in MCMC algorithms. So that's just the overview of the talk. So I'll just start sort of in a very, let's see, this doesn't work, okay. So let me just start by mentioning all the people who are involved. So this is Rahul. So he is currently a core developer of Shogun, right? So he's doing this Google Summer of Code project on basically block-based two-sample tests and feature selection using kernel embeddings. And so through this and previous year's project in Google Summer of Code, he became core developer. And a similar story holds for Heiko, who's now running the show here. He also got into Shogun through Google Summer of Code, and basically this I will also get into some of the stuff that Heiko implemented in his Google Summer of Code project. So myself and Heiko were working with Arthur Gretton at the Gatsby unit. He's a professor there, and basically he's the godfather of this idea of embeddings of probability distributions into reproducing kernel Hilbert spaces and then doing things there among some other people, obviously. So, okay. So let's start with this example. Say I have a data that looks like this. I have pictures of dogs, and I have some descriptions of these dogs. And I want to test the hypothesis that these descriptions of the dogs are dependent with these pictures of the dogs. Okay, so it's a toy problem, but nice, a nice example to illustrate what kind of problems we're considering. So if each x was just a sample from a Gaussian random variable, from a Gaussian distribution, each y was also a sample from a Gaussian distribution, we want to detect dependence, we would just compute correlation between these two, and that's basically it. That's how we detect dependence between x and y when they're just Gaussians. But now we're dealing with some domains that are not really easy to deal with. So we deal with pictures and we deal with text. So what do we do? So basically, hypothesis that we're trying to test is, well, these descriptions are saying something about this thing here. So, and we will try to detect dependence between them. In a sense, we will look at the phrases that appear here and see whether the phrases like couch potato appearing in different texts are associated with pictures that look similar in some sense, right? Okay, so how do we approach this problem? Well, kernels are the solution. So we pick our favorite kernels on pictures of dogs. So Marius discussed how to actually optimize these kernels, so I don't really have to get into what are the good kernels on dogs, but you extract some features and at the end you get some kernel. And you also have your kernel L on the text domain. And basically what we do, we have our samples of pictures of dogs, samples of their descriptions, and we form these kernel matrices. All right, so what do these kernel matrices do? So each entry here, xi, xj, so this is basically measuring a similarity between dog I and dog j. Yeah? So you can think of this kernel matrix as some kind of similarity pattern in your set of samples of the pictures of dogs. And then we have another similarity pattern. This is similarity pattern between these paragraphs of text. So what is sort of an intuitive notion of measure of dependence between these two data sets? Well, I ought to look at some individual entry here in the kernel matrix, k, xi, xj, and see whether when that entry tends to be large, the corresponding entry in the L matrix also tends to be large. So that will indicate to me that this similarity between pictures of dogs is somehow coupled with the similarity between these paragraphs of text. Okay? So I have two similarity patterns, so what I'm going to do, I'm going to compute a similarity between these two similarity patterns. So that is just an inner product. So if I center these two kernel matrices in a particular way, then I'm just going to compute their inner product, and this boils down just to the trace of the product of these two kernel matrices, trace KL. So it's a very intuitive notion of dependence between these two samples. Okay, and now I will introduce a formalism which basically tells you what does this specifically mean and where does this arise from. So it arises from this notion of embedding of a probability distribution into a reproducing kernel Hilbert space. So you can just think of it as a Hilbert space. These reproducing kernel words are not too important. Okay. So Marius already discussed sort of what a feature map is and how does it relate to this notion of a kernel. So when I have some data point, individual data point, say x, I can extract individual features of that data point. Right? So I can maybe take x squared, or if x is vector, I can look at the products between the individual entries in x. Those are some features, some measurable quantities that are related to this individual data point. So I can do that. I can extract this vector of s, length s. This lies in this Euclidean space. It's our vector space that we know and love. So it's a finite dimensional space. So what we do, instead of extracting this explicit feature representation of a data point, we consider some abstract representation that lies in this Hilbert space. It's just some function. So just kernel with one argument fixed. So only thing I care about this object is that I can compute corresponding inner products easily. Because inner product between this feature representation and the corresponding feature representation of a data point y is just this kernel evaluated at xy. So that I can compute, and I don't really care what the explicit representation of this thing is. It could be infinitely dimensional in all, and indeed in almost all interesting cases it is. So I'm kind of doing inference in an infinitely dimensional space, but because of this kernel trick, I do not need to work with these explicit representations. Okay, so that's all we care about. Inner products can be easily computed, and then we can do things like this. We can have this sort of classification problem where decision boundary is not linear, and we can map it into a feature space where it is linear, and then map it back, and we get nonlinear decision boundary. So a good old SVM that we all know and love. Okay, so embedding of a probability distribution just takes this one step further. So now I'm going to take a probability distribution P, and I'm going to take expectation of these features k dot x over this probability distribution. So now I'm taking an expectation over some space. It's potentially infinitely dimensional, but I don't really worry about that. Under some very weak assumptions, this always is well defined and exists. And it's again just some point in this Hilbert space. Okay? So I denote that by mu kp. And again, you can think about that as extending a kernel trick a bit further. So now, rather than explicitly extracting some features of the distribution, maybe the mean, covariance, third moment, whatever, all these kind of things. Maybe mixed moments if a distribution is over multivariate space. So rather than working with this explicit representation in terms of moments, which gives us our parametric representation of probability distributions, I work with some functions that live in space HK that is potentially infinitely dimensional, but I do not care about explicit representations. Okay, so now again, a kernel trick follows here as well. So now when I actually look at these inner products between these individual embeddings, this is just the expectation of the kernel function evaluated at x, where x comes from p, and y, where y comes from q. Yep.
So when you make the analogy to the moments view, then I guess you choose phi I as a Monod function.
Yes, precisely. Yes, precisely. I should repeat the question. So when we're using this explicit representation, then this is just a scalar, effectively. So it could be something like if x is just a scalar, it could be just its mean, its second moment, third moment, etc. And actually, if you're using a polynomial kernel of order s, you will exactly recover this. If p is over a higher dimensional space, then this could be joint moments. Okay. So what I care about is that I can easily estimate these inner products. So basically, I just take these probability distributions, I map them into this Hilbert space, and I compute distance between them. So that gives me a notion of distance between these probability distributions. That is, because of this kernel trick, easy to estimate. Okay. So so this notion is actually called maximum mean discrepancy. This is a notion of distance between probabilities, and it has a nice interpretation that it is basically maximizing pulling apart expectations with respect to these two probability distributions of smooth functions. So I'm going to say a little bit more of what I mean by smooth functions. But this is basically what we do. This MMD, just distance in this Hilbert space, but it also has this interpretation. Okay. So, and almost all kernels that are popular in machine learning that we know and love, like Gaussian, Laplacian, Matern, and so on, this is actually a proper notion of distance. It's a metric in a mathematical sense, in a sense that it is actually equal to 0 if and only if p is equal to q. So regardless of how these two distributions differ at whichever moment we want, it is always equal to 0 if and only if they're equal. Okay, so but that's a technicality.
The other conditions on the kernel.
Yes.
Universal kernels. Right?
Yeah, so this is a very similar notion to universality of kernels. It's not equivalent. So basically, universality implies characteristic kernels, but characteristic is just slightly. It's very, very technical, the difference between the two. Okay, so I have now this nice notion of distance between probabilities. And why do I care about these smooth functions? Well, when I have samples that look like this, so this is a sample from Q, this is a sample from P, and I want to say whether they are different in a statistically significant way, well, then I can look at all these functions, all these smooth functions that I can draw, which pull apart these expectations with respect to Q and with respect to P. Okay, so in that sense, this sample is more different than that sample, than this sample is more different than that sample, right? Because here I cannot really draw a smooth function such that expectation with respect to red points is different than the expectations with respect to blue points. Okay, so which captures intuitive notion that this sample is more different than that sample, then this red sample is more different than that blue sample. Okay, so because if I didn't have smooth functions, if I just consider bounded continuous functions, for example, I can always draw pathological cases like this, where any two samples look equally different, and I don't want that. So it's really this smoothness that's regulated by the choice of the kernel that will basically tell you how smooth these functions are. And we'll see later on an example of why this matters. So So basically this is just writing down this kernel trick. So I can take this notion of a distance between probabilities, I can expand it in terms of expectations of the kernel function in the following way. So now this is just some set of expectations, set of means of some quantities that I want to estimate. Then I can plug in a minimum variance unbiased estimator. So that's the smallest variance estimator here that is actually unbiased. So its expectation is the true quantity. So that is an estimator that you would use if you have a limited data, unlimited time scenario. So you have just a certain number of points nx from P, certain number of points of ny from Q, and you want to have an estimator of this quantity that is best in a particular specific sense. So you would use that. It requires a quadratic time in the number of samples. So n here denotes nx plus ny, for example. So that would be the strategy in this regime. If you have a different type of regime, so maybe you're streaming some data, so you have unlimited data, but your time is limited, then you can use various different estimators, and the simplest possible way to do this is basically just to process your data, your samples as they come in blocks, and then compute this minimum variance unbiased estimator on these blocks, and then average them together. So basically, B, the size of the block here, is something you can tweak, and basically that gives you the trade-off between complexity and the statistical efficiency of your estimator. Okay. So now that we have this nice notion of distance between probabilities, we can use it to formulate a statistical hypothesis test. So now I don't observe these probability distributions directly, I just observe samples from them. So every time I see new samples, my estimate of the distance between these two generating processes will be different. And I can try to test the hypothesis that this distance between probability distributions that I've computed is larger than what can be attributed to chance. So I'm testing whether there is a statistically significant difference between two generating processes. One of them generated X's, one of them generated Y's. So our null hypothesis is that they are the same. Our alternative is that these two generating processes are different. We observe these samples, and then basically we compute these values of the statistic, hat M and D. And if this is further from 0, then what can be attributed to chance, that we will reject the null hypothesis and say, well, this is true instead. Otherwise, we do not reject the H note. So this is then still a working hypothesis in our model. Okay. So there's a very straightforward way to now generalize this to a framework that I've discussed in the beginning. I want to now test independence between two data sets. So now I'm observing paired observations, X's and Y's. They come together jointly, maybe pictures of dogs and their descriptions, and I want to test whether they are independent. So our null hypothesis becomes that they are independent, alternative that they are not, and you can just write this in terms of joint and the marginal distributions, and this becomes very similar setup as we've had in the two-sample testing before. Okay, so in this case, what we're doing effectively is we're computing distance between these two probability distributions, joint and the product of the marginals. So now you will notice that this is a probability distribution on the joint space of pictures of dogs and texts, right? So I need also a kernel that operates on the joint space. But that's easy to do. I can just basically multiply individual kernels on these individual domains. So as long as I have a kernel on docs and kernel on the text, I'm fine. Okay? And what happens is that basically when you estimate this quantity in exactly the same way as we've done before, when we had this MMD hat, we exactly recover this intuitive notion of dependence between two random variables that we've seen at the beginning. So it's exactly a measure of similarity between similarity patterns in these two samples. Okay. So, and this gives us a very nice framework for independence testing. So how much time do I have?
Just
maybe 15 more minutes? Okay, excellent. I can then press on. So how are we doing so far? Any questions? Any issues? I can, since I have time, I can like go over things more slowly if you like. Yeah.
Maybe you can give a bit more insight to the MMP. I mean, there are other ways to compare probability, right? For example, KL diversion. So how do they relate?
Yeah, sure. So that's a great question. That's basically a crucial question. So we have this notion of distance between probability measures. How good is it? What is it capturing? So short answer is that it depends on the kernel very much. So because it's basically just looking at these expectations of the kernel function. So there are some results, obviously, that tell us that KL is an upper bound on this notion of distance between probabilities. So it has this nice interpretation in terms of, in this form, which puts it into a family of distances between probability measures that are called integral probability metrics. And basically, by just varying this space of smooth functions, you can recover various other distances between probabilities in the literature. For example, a Dudley metric, Kolmogorov-Smirnov, Wasserstein distance, they're also members of this family. KL is not. KL is a member of phi divergences, so it's not in the same not in the same family. So, but what is the crucial point about this notion of distance is that this is something that we can estimate very easily, and the rate of our so basically, and the asymptotic efficiency of our estimators does not, well, this is kind of controversial, but does not really depend on the dimension of the underlying space. So it is, I mentioned it's controversial because actually it is correct, but the point is that this notion of distance will actually drop with the dimension of the underlying space, but the actual variance of the estimator will not depend on the dimension. So it is something that becomes less useful as we increase the dimension of the space, but it's still something that's easy to estimate in the situations where we do not have alternatives, because KL becomes horrible in high dimensions. Any other questions? Okay, so let's press on a little bit. So let's see. So we're here, right? So now, in this framework of hypothesis testing, so we are basically looking for statistically significant values of these statistics. So what we have to consider is what is the distribution of this statistic, of this estimator, under the null hypothesis that P and Q are actually the same. So it turns out to have a very ugly form. So it is an infinite linear combination of some chi-squared random variables. So just something that is very difficult to compute quantiles of. And not least because actually these coefficients will depend on your kernel K and on the underlying distribution P. So we have to basically do some kind of approximations of these null distributions to do the test. And I've listed here just some three most common ways to do this, and one of them is just permutation test, where we would, for two sample testing, just merge the samples from P and Q together and then split them randomly into equal proportions. So this is by construction now a sample from the null, because by construction now P and Q are the same. They come from the same generating process, because I took these two generating processes that may or may not be different, and I've just created a mixture of these two, and I'm sampling from that. Okay, so that gives you a sample from the null, and you can do as many of these shuffles as you like, and basically then estimate your p-value to whatever confidence you want. Okay, so that is two sample testing. So I'll just briefly discuss three different applications. So t-tests are basically a special case of this framework, if you will, because in t-tests we're just looking for differences in means. And here we're looking for differences in a non-parametric fashion. So differences can occur at any moment. For example, if you're doing some data integration, you're wondering whether you can train your model on the merged samples or whether you actually need different models to train. Because there are statistically significant differences between your two data sets that come potentially from different sources. Or you can, for example, do things like interpreting cluster analysis. So this is a nice example here. There's a hierarchical clustering algorithm on these different types of cancer cells. And most of the types of cancer cells actually are well separated with this algorithm. But these two types cannot be separated by standard hierarchical clustering algorithms. And then we can pose a question, well, is this a problem of the algorithm? Is this just something that we are not somehow using information that exists in the data and we cannot obtain the right clustering in some sense? Or is there really no difference between these two data sets? And this paper actually did this kind of non-parametric two-sample test and showed that there is really no reason to believe that there is difference between these two data sets. Okay. And so that was two-sample testing, and in the context of independence testing, you can also consider feature selection, because now you have a measure of dependence between random variables, and whenever you have a measure of dependence between random variables that is expressive enough and that is easy to compute, basically you can try to approximately solve this problem. So what does this problem do? I'm going to take my set of features, there's S of them, and I'm going to pick a subset T of much smaller size that maximizes this dependence between these features in T and my response variable. Okay? So this is a combinatorial optimization. It's very difficult to solve, but we can use various heuristics that are available in the literature. So this is also something that's being currently implemented in Shogun. So maybe so in the interest of time, I might skip over that. So like, this is just making a point that the choice of the kernel is very important, because sometimes a difference in these two generating processes might exist at a scale that is not somehow a global scale of your distribution. So here I have two distributions that look about the same, so they are all mixtures of 9 Gaussians, but just the covariance in each individual component is rotated. So a difference basically exists at this length scale, not on the length scale of the whole distribution. Okay, so and then there's basically other topics you can do with this tool. So you have a way of representing probability distributions. You can test for various things. You can test for conditional independence, for other forms of interaction. Maybe you have a graphical model where you have two independent causes that very weakly influence a third variable individually, but jointly they combine in some nonlinear way and form a strong effect. And this is a tough situation to test, because if you do individual independence tests between these two, you might not see that there is actually dependence. Okay, and there's various other flavors of how you can utilize this methodology. So just as a conclusion, kernel embeddings are awesome. So they give you computationally efficient ways to do fully non-parametric testing. And in Shogun, we have this flexible and modular framework for doing these things that has been implemented in this Google Summer of Code project this year. So I don't know how much time I have, but I could...
About 5 minutes.
Maybe 5 minutes. Okay. So I can just show you a little bit of how this works in Shogun. So basically here, I'm just gonna load Shogun, as you all know. So I'm dealing with this example that I've mentioned, where I have these mixtures of Gaussians.
Can you maybe zoom in a bit?
Okay. So here I'm gonna set basically, because this will be a linear time test, in a sense that we will operate on streaming features. So we are in the unlimited data, limited time framework. So basically, Shogun has this nice way of defining streaming features. So you basically just have this generator, which is just something that you give it a number of samples, it will just produce you those that number of samples from this generating process. You can equally just look at a file and read it sequentially. Okay, so now I just defined this generator. So this is some built-in Gaussian blobs data generator in Shogun that we consider for these tests. And these are now my streamed features. So this is the streamed features, streaming features instance, and then I will just get actual X here, and I will plot it, and they look like this. Okay. So typically, when we do kernel methods with Gaussian kernel, we set bandwidth to what is called a median heuristic. So we would just basically look at the distances between the individual samples and take the median of them, and this will be a good heuristic for the scale at which things happen in this data set, in a way. So as I mentioned here, you have this global scale, and when you compute it, oops, so I didn't actually execute this. Okay, and when you compute it, you get a number that looks like that, so it's about 200. So now what I'm going to do, I'm going to just define this instance of this linear time MMD estimator that will allow me to do a test. So you will notice I will passing streaming features to this, right? So you can just work in the limited time, unlimited data framework. So then I have some freedom to choose ways in which I'm going to approximate my null distribution, how I'm going to estimate the variance under the null hypothesis, these kind of things. So, and I have to emphasize that this is basically the only software currently where you can do this in a nice modular fashion. So Shogun is basically, if you want to use these tests, Shogun is the way to go. Okay. And so now what I'm going to do, I'm just going to run 10 times the estimation, so I'm going to use 100,000 samples from each, and 10 times I'm going to run the estimation of this MMD. Every time it produces a different value because it's defined in the streaming feature, so we just take some portion of the data and discard it, forget about it, every time it's different. And you see that the p-value, even though I've generated these two data sets from two different generating processes, are very large. So we're not actually rejecting the null hypothesis. Okay, and you can also see it here. So when I do 10 tests at the significance level 0.05, so I will almost always basically reject the null hypothesis. Not reject the null hypothesis. So there is not enough data somehow at this scale, at this bandwidth, to say that these two generating processes are different. So whereas here I'm going to actually optimize my, where am I? Oh. So now this is running an optimization over MKL, exactly as in Marius's talk, over a set of basis kernels that all have different bandwidths, and I'm going to find a weighted sum of these that directly maximizes the power of this test. So I'm exactly maximizing the criterion that I care about, and this turns out just to be a quadratic program, and I can do that. So it takes a while. I have about 12 kernels there, and it's quadratic in that number. Never happened. So we got some nuns there. But basically, I've run this before, and you see that here, you know, when I ran it with this optimized kernel, it gave you much improved power in this sense, in this case. So, not sure why nans happened. So look here, it goes through this time. Yeah.
I have multiple questions. First of all, you really use a vector combination?
Yes, yes, precisely.
How do you find the coefficients?
Oh, it's just a quadratic program. When you write down the power of the test in this setup, it ends up to just being maximizing basically the value of the statistic over its standard deviation.
Okay, so the first
The first question was how do you optimize the kernel coefficients for this weighted combination of kernels that I talked also about in my talk? Yeah, and this was the answer.
Yeah, so exactly, the answer was just, it's just like in the case that you've presented, just a quadratic program that we run.
And the second question is, how do you correct, in this case, for the, how do you calibrate the type 1 error? Do you do it with permutation test here? Or?
That's a very good question. So you spotted a potential issue that might arise, that if you actually do this optimization and do the testing on the same data set, your test is no longer correct. So that's absolutely true, because your choice of the kernel depends on the data. But because we're in this streaming scenario, we basically optimize the coefficients on a different data set. So first there is this training data set on which we optimize the choice of the kernel, and then we actually test on a separate data
then
set.
my suggestion would be probably you could do the permutation around the whole pipeline also.
During the whole pipeline.
Around the whole pipeline, yeah.
So that's interesting, but I'm not sure that it would solve all the issues that might arise in this dependencies that arise between the kernel choice, and because basically then your null distribution will not be correct, the one that you're estimating. It will have a much higher variance when the kernel depends on the data on which you actually compute the statistic. So permutation might not...
That's why you do the permutation around the whole procedure.
Yeah, maybe we can talk offline. I may not understand exactly what you mean over the whole procedure. All right, cheers.
I think the thing is, so
what we're using to the fact that we're exploiting to learn the kernel is based on a certain parametric form of the null distribution. And if we do this, what you say, we could do the permutation testing, we could still do the test, but we then can't optimize anymore. We lose this expression that we're optimizing. It doesn't maximize the test power anymore. That's why we can't do it.
So when we basically use the fact that in this case, when we have this block-based approach, the statistic ends up being asymptotically Gaussian. So then you can actually look at the power, asymptotic power directly, look at the equation and try to optimize it. When it's this ugly form of infinite, infinite combination of chi-squares, you cannot do that explicitly. Okay. So yeah, so it's done now, so it's not nonce, so there is hope. And basically, I've done this kind of now test with this other kernel before, and you see now that it will start rejecting the null hypothesis. It actually found the right scale at which these two distributions differ. So it's much more often too. So that's basically it. I would, I guess, conclude there in the interest of time and leave time for any other questions.
So how many points are you running this on?
100,000 from P and 100,000 from Q. So yeah, it's running pretty fast. Dimensionality here is 2 because they are exactly these data sets. Yeah. So it's.
I was very impressed.
Well, we did run it on some very high dimensional data on some music examples. So we were able to test for differences between 2 songs from Rammstein. Of course, it's a real data set, real world data set. So, and I think there the dimensionality was about 10,000, if I remember correctly. Yes. Any other questions, comments?
So you mentioned in the title of your talk also feature selection. I didn't see this.
Yeah, so I very briefly, had only one slide on that. So it is currently being implemented in Shogun, so I had a small tutorial here as well on this. So basically it just boils down to computing the estimates of this HC quantity, which is basically just the MMD between the joint and the product of the marginals, and running a backwards elimination over the features, basically discarding those features that have a small HSIC value. And so the student is implementing this in this year's Google Summer of Code. So we're still working on it. There's still a few things to tie up. It's not ready for the release yet, but it will be very soon.
Precisely,
yes, precisely. So this is a paper by Lee Song, I think, from 2009 in GMLR, feature selection via dependence maximization. So it's a standard technique using backward elimination. You can also use forward selection if you will. So the point is that when you're actually computing this dependence, you're always doing it jointly over the features that you currently have, so you don't miss actually any dependence that might arise from nonlinear combination of the individual features.
Thanks for the talk. This might actually be a dumb question, but suppose I'm not an informatics guy working on big data, but a psychologist with 60 samples. What do I do? Would it still work?
You use minimum variance unbiased statistic, and it still works.
Okay.
It still works. There are some. The way in which you would optimize the kernel choice is slightly different in this context, but it still works out. So this actually is not in Shogun yet. It's still part of the ongoing research, actually, how to exactly do these things. But it follows through. Okay, thank you very much.
Thank you so much, Dino, for the talk. And the second talk of the afternoon is by Ian T, who is a postdoc also, but this case in EPFL, is that right? And he's going to be talking about variational learning for recommendations with big data, if I got that correct. Yeah, sort of. And it's also, I believe, an ongoing project right now of Google Summer of Code that he is mentoring.